Okay.
Okay.
Thanks. What? Yes. Okay, good. So I talk at this thing essentially, or this is where the microphone is, right? Okay.
Well, you can stay relatively close. I mean, you don't need to be really attached to it. But let me stay here so I can introduce you.
Okay.
Some poetry, yes. Okay, shall we start? Okay, well, welcome everybody, and thank you for coming to this APARCOS-seminar. And it's a big pleasure to having here Tony Mroczkowski, who is coming from ISO. He's an astronomer there since 2016, right?
Yes.
An instrument scientist, sub-millimeter instrument scientist. Before that, he got his PhD in astronomy in Columbia University, right, in New York, with a thesis that mixes instrumentation and data exploitation of data.
Yeah.
So that far, Sunya-Esaldovich array.
Yeah. Lots of fun stuff.
Yes.
Instrumentation and analysis.
And data analysis of Sunya-Esaldovich science. He got a postdoc at the University of Pennsylvania, also working in several instrument developments there.
Yeah.
He was an Einstein Fellow at GPL, Caltech, and he was working on the design of the CCAT project by that time.
Well, I mean, most of the other people designed it already.
Yeah, no, but I mean, together with...
Yeah, I was working on some instrument prototypes for that.
Okay.
And
well, he's one of the core scientists and specialists in instrumentation of the AtLAST project, which is the talk that he will tell us about, and in which we participate also here at UCM as a part of the collaboration. And likely I can say that he recently got one of these ATRAE contracts that he recently was awarded, and he will be here at the Instituto de Ciencias del Espacio in Barcelona, starting fall, no? By fall this year.
September 1st.
September 1st. So we will have him closer, and it's a good acquisition for the Spanish community to work on AtLAST in the future. So welcome, and yeah.
You have for those to learn Catalan, no?
What?
You have for more to learn Catalan.
Yes.
Yeah. Almost. It'll be fine. So yeah, thanks for having me. And yeah, I'm looking forward to engaging with the Spanish community more and being nearby. So I'm going to talk about the Atacama Large Aperture Submillimeter Telescope. Has everybody in this room heard about it, or probably no? Yes? Okay, great. And then there's a disclaimer here, the project is funded by the European Union. The views and opinions expressed here are by me. They don't reflect like what the EU said, so don't hold them accountable, I guess. We're required to say that, but right, and then this background image that was created in this tool called PySM. I should give credits there. So it's a sub-millimeter microwave emission model, and it's too low resolution for AtLAST. Actually, you can see some like pixels in there and everything, but it's more for CMB foregrounds. But it's still a very pretty picture of the center of the galaxy going over the Atacama Desert. And this is not advancing. No. Something happened.
Yes.
Okay.
Now.
Okay, great. Yeah. So this was our initial design study. This wrapped up in August of 2024, and it had 6 work packages. That's what WP means here, and then a working group on instrumentation. That was unfunded, but an in-kind effort to look at the prospects for instrumentation. I was leading the telescope design, so that was aimed at covering a broad elevation range, able to point all the way up at 90, point close to the horizon at 20 degrees, and cover all of the frequencies covered by ALMA, essentially, and slightly lower. Notably also a very large field of view, 2 degrees. So ALMA in its higher frequencies is just a few arc seconds of field of view. So very tiny. And then we aim to put it in the Château Plateau. Fran here has been very involved in the operations, so one of the co-leaders of this group, really looking at how we're actually going to run AtLAST and deal with the data rates and everything. And, a bunch of other things, like governance and coordination, of course, and the science case resulted in 8 science papers that were actually refereed on like a lot of science white papers and science books for other observatories. So our science cases are distilled as 3 major drivers. So where are all the baryons, so all the normal matter in the universe, so measuring the dust and total content of the Milky Way and other galaxies. The really cool thing about millimeter and submillimeter is you see the coldest gas that's, tens of Kelvin, and you also see the hottest gas that's, at 10 to the 7 Kelvin, 10 to the 8 Kelvin, and this is scattering the CMB, and this is stuff I work on, so this is my own pet thing that I get excited about, the SC effect. But it basically sees just a broad range of all this stuff that's invisible in the optical, truly invisible in optical wavelengths. So that's really cool. And then understanding how structures interact with their environment, at these wavelengths, you see the turbulence and magnetic fields, and you see all of the cycles of all of this hot and cold and intermediate gas going in and out of galaxies and forming stars. And what does the time-varying sky look like in the submillimeter? So this hasn't been explored very much, and all sorts of events are, they show up first at millimeter and submillimeter frequencies, including solar flares at the very beginning of the solar flares. They're very bright in millimeter and submillimeter, but also a lot of things like black hole variability. It's less opaque at these frequencies because inverse Compton limits it less at these frequencies. So there won't be a quiz on this. AtLAST science drivers, so the galactic ecosystem. This is basically showing. Move the cursor. I guess it doesn't matter. This is showing what the LMT sees at 1.1 millimeters. So this is a large 50-meter telescope in Mexico toward the upper end of its frequencies. But as you go to higher frequencies, you get more resolution with the same dish. And that's something that you can do from the AtLAST site. And then, this just shows multiple scales going across instruments from ALMA at the highest resolutions to Planck at the lowest resolutions. But there's all sorts of self-similar, almost fractal scale structure in the sky. Another science driver was completing our view of galaxy formation through wide surveys. So all of the things, optical usually limits out at about redshift 2.5 or 3, but we can actually, through the dust and molecular gas emission, probe out to maybe redshift 8 when we first start getting pollutants in galaxies like dust and molecules. So that's really cool. That's really a complement to things you might have seen from JWST and all of that, and all of the radio frequency surveys. And then also, covering the baryon cycle, the connection between their extended circumgalactic halos. And this is just showing what lines are detectable as a function of frequency and a function of redshift. So if these lines exist, we can just probe them in our bands out to arbitrarily high redshift and really probe the formations of the first galaxies and all of that. This is my own pet science case. So I work on the Sunyaev-Zel'dovich effect, and this is the hot gas in galaxy clusters and galaxy groups. So basically, you have the CMB at, it's a cosmic microwave background. It's truly coming from all directions, and it gets scattered by hot gas in the halos as it goes through. The photons go through, and they get scattered to higher energies, and we detect them. But basically, this is what the gas pressure looks like in SZ. This is in the kinetic SZ, which is a distortion based on the motion of the gas. And this is what it looks like at X-ray. So X-ray, you have to go to space to see this view. But we see a pretty similar view if you go to high enough resolution from the ground. And then we can also probe the gas motions through this novel effect. And both of these two Sunyaev-Zel'dovich effects are redshift independent and surface brightness, which makes it very powerful at high redshift. Most things get dimmer as you go to higher redshift, and this doesn't, which is very unique in astronomy in general. so that's just showing a simulation of what you would see. Mustang 2 is a small instrument on the Green Bank telescope, 100 meter, and it would only see a portion of the field and, at a fairly noisy view. And this is what ALMA would see. You would see just this tiny little circle in there in a deep dedicated pointing. And these ripples would actually be from a shock front in that galaxy cluster, so they'd actually be meaningful.
We are recording the seminar, so maybe
Yeah.
to point directly to the screen, so people, if they
Oh,
see it
no,
after
no.
work, can follow you.
Sure, sure. So this tiny ALMA field of view, and it's a tiny circle, you might not even see it under. Those ripples are meaningful and everything, but this would be what AtLAST would see, which is a modest instrument of a few thousand detectors. So it's clear that you get the big picture out of AtLAST. And then, going further, so adding in, we also have solar cases, so we can actually look directly at the sun and map the emission from the sun. But basically, if you're interested, just check out, these 8 light reading science cases. It's only about 300 pages of science case, but it's covering a huge swath of astronomy and providing a view that you just don't get in the optical. So it's all very complementary. And this is just a slide on the solar science case. So, this is what ALMA saw at 3 millimeters with its total power array, and this is the input simulation, that matches that. This is what you would see at the same frequencies with AtLAST, so it's a lot higher resolution. And of course, if you go to higher frequencies, you also get higher resolution. But it's also very meaningful, as you go across the bands, you see deeper into the solar atmosphere, and you can probe the chromosphere and photosphere and all of this lovely solar physics stuff. So yeah, and actually the European Solar Telescope EST is a partner now in AtLAST, so I guess they recognize the value of the complementarity there. So I guess bigger picture from the telescope standpoint, this is what the field looks like for sub-millimeter and millimeter telescopes. You'll probably recognize a few of these. This is in Grenada. This is the IRM 30 meter. This was in Hawaii. This is actually shut down. That's Apex. This is the South Pole telescope surrounded by a nice broad plain of Antarctica and not much else. Atacama Cosmology Telescope, that's now shut down. But basically the whole point is most of these are southern hemisphere, apart from a few. None of the large dishes go above 350 gigahertz. Basically you don't get observations with the LMT or IRM above 350 gigahertz. And nothing over 15 meters exists in the southern hemisphere. So this is really unique to talk about 50-meter telescope that goes up to a terahertz in the southern hemisphere, like AtLAST. So these are technical requirements. The wavelengths go up to a terahertz, 50-meter, large field of view. We want to have at least 5 instruments to serve these various science cases. Some of the science cases demand the same instrument, so you can do the same science with multiple. You can do multiple science cases with one instrument, which is good, because you can serve a broader community that way. We want a fast scan speed, so we can modulate our signals fast. If you have like a few hours, I can talk about that with you. And then the mechanical pointing accuracy is pretty high. This is uncorrected, so for typical astronomical models, you can correct to 5 to 10 times better than that. So that's good. And then this is just comparing the AtLAST site to other sites. So, right. This is the Chachanantor Plateau, where AtLAST would be. Cerro Chachanantor, this deeper sort of indigo blue. It's got slightly better transmission, but it's up at 5,600 meters, so it's really hard to work up there. There's not that much space to put a 50-meter telescope, and the Chilean labor law basically limits you working up there easily. So we're going to good enough. The transmission is good enough at the AtLAST site for these high bands. This is a good transmission compared to everywhere else on the world, essentially, and we want it to be reasonable and low risk. The work packet, the operations plan, so talk to Fran about this, but basically they've been studying how to operate this, how to manage it, how to coordinate remote observing, so you don't have to send people there all the time, you know, have a huge carbon budget with travel and getting people out there, and, you know, and how to deal with the massive data rates and all of that. So Fran can answer all these questions there. I focus more on the design of the telescope. So I was heading the instrument team, the optics experts, the engineers and all of that, actually doing the design of the telescope. So we aim for a 20 micron surface accuracy, or 30 microns during the daytime. So 20 microns at night is our best. This is a factor of 1,000 worse than optical telescopes. We know we can do it, technically, because optical telescopes do it. For instance, the 39-meter ELT is focusing to 20 nanometers, a 39-meter dish. So, you know, that's good. But this is basically the transmission, this is the aperture efficiencies for those two, and comparing it to the atmospheric transmission, you can see the transmission is mostly the limitation for getting these for getting observations at these frequencies. So we think we're in a good place with this design goal of 20 microns at night and 30 in daytime for our efficiency. And then this is just placing the telescope in the context, the landscape of what exists. So I don't expect everybody to know the acronyms here, but AtLAST is that star. So it's got a nice big primary compared to all the little ones. It's got a respectable field of view. So it's not the biggest one out there. The biggest ones out there are these survey telescopes that are sort of 6-meter to 10-meter class dedicated survey instruments. But when you combine the two, you get the throughput, or étendue, and that is, you know, a good factor of 5 or 6 higher than the best survey telescopes happening right now. So that translates into a huge mapping speed. And I just added this plot, so that throughput is here, A omega is there, and that's now here, right? When you combine it to this figure of merit that's in the typical Rolfs-Wilson, Hüttemeister, Tools of Radio Astronomy book, this basically scales like mapping speed, and we're just by and far away, you know, 2.5 orders of magnitude faster mapping speed than the dedicated survey instruments for mapping. And meanwhile, I normalized this so that ALMA is 1 on here, and we're at the, I don't know, 5,000, 6,000. So we're just incredibly fast. Sorry, maybe that's, yeah, I think that's right. So just incredibly fast compared to what ALMA can do at these frequencies in terms of mapping the universe. So ALMA is more like a microscope that you would use for following up and getting very detailed pictures. AtLAST will be able to look at the whole sky, the whole universe, and really tell us what's going on and discover things. And similarly, the resolution is well matched to some of the premier instruments at other wavelengths, and providing, you know, similar resolutions to many of the other things. So that's also really nice. How do we do that? The optics are this novel design where basically we keep everything on axis and compact as possible to keep the telescope structure cheap. The more off axis you go, the bigger the telescope structure actually is. So that costs more money. And we keep the optics fast. So bring the beam into from the primary, mirror 1, to the secondary, mirror 2, very quickly, and then have a simple folding mirror that brings it to the instruments, brings your rays of light to the instruments. And that folding mirror, it tilts on its axis, so that selects your instrument very simply, which is really nice. This is what the design looks like. So it's similar to some of the other designs that have come before it, but you'll note it's a big, there's this big wheel here. This is basically called a rocking chair design. All of this space behind it is receiver cabin, essentially, and internal structure. So it's just a huge amount of area behind the telescope, and, you know, closing dome for inclement weather. This is a truck. That's a real-size truck, so it's not a toy, you know, for scale. And then this is what it looks like inside. So you'll see this structure is called the elevation wheel. So it moves the telescope in elevation. This is on a fixed platform. So we have 2 of these large instruments. By large, I mean up to 5 meters across in diameter. And then we have 4 smaller instruments in there that move with the elevation wheel. So when you tilt the telescope, the receivers will also tilt. They'll be mounted and they can slide around or anything. Those are our smaller instruments. Those are the red ones. So those are only 2.6 meters in diameter. So for comparison, each one of these can be about the size of a shipping container, and then this is the size of 4 or 5 shipping containers. So just gigantic compared to the typical state. But as Fran will tell you, in comparison to Apex, you often have 7 or 8 relay mirrors before you get your beam to your instrument. This is super simple. You just have one mirror that moves and it brings the beam to there. So it's super easy to understand what's going on in the telescope. The other thing is we studied the optics, obviously. This is what the diffraction limited field of view looks like natively. So you'll notice it gets very small at the high frequencies, right? And this should be a little bit disconcerting at first. Basically, that I tell you we're going to have a 1 to 2 degree field of view, and it's only half a degree at the high frequencies here, at the short wavelengths. But this clever postdoc, Pato Gallardo, studied the optics things and came up with optical solutions that are similar to what's being used in CMB-S4 and Simon's Observatory and other premier instruments. But basically, you break up this highly curved so-called focal plane, which is not a plane, into a bunch of little cameras, and you put corrective optics in each camera, and you can recover, at the lowest frequencies, you can recover the full field of view, you recover most of it. So you want to have these values above 80 here. That's 80% or 0.8 Strel ratio. Means your diffraction is negative. And as you go to higher frequencies, you can recover still a significant portion of the field of view, especially if you're willing to relax your Strel ratio a little bit. But at the high frequencies, going a factor of 10 in frequency means you have a factor of 100 more detectors to fill that field of view. So having it slightly smaller at the high frequencies is not a problem in terms of beams on the sky and mapping speed. So it's still transformative level. These are what the beam properties look like. So I work in CMB a lot, and people were worried about these on-axis optics delivering a beam that would be bad, especially in terms of polarization. So often in CMB, you build an off-axis telescope with a nice clear unblocked aperture, and the idea is that this will have a nice polarization. So we studied that. We studied what the panel gaps do to our beam, what the struts do, and here you can see the ideal case, so no struts in the simulations, no panel gaps, no surface RMS, anything, right? When you add the panel gaps, you see basically no difference. You should see basically no difference. When you add the struts, you see this pattern here, but that's down by about 60 dB, so it's a 6 orders of magnitude lower type effect on the beam. So you're never going to notice that, essentially. And in the cross pole, you still see no difference in the polarization response. When you add the surface RMS, that's when you start to see an effect, and that's something you can't avoid. That's something you can't avoid as well in these nice survey instruments. They also have a beam that gets a little bit nasty when you start to add the surface RMS. But basically, the beam is well behaved when you add the RMS. So these are the beam comparisons in there. So 0 would be the yellow curve. That would be the ideal case. The beam is essentially the same, and it's really, when you get out very far, you start to get some noticeable effects. But you have to go about 40 dB down, so 4 orders of magnitude lower than the primary response. So that's good. That basically means that you could do any kind of polarization measurement you want with AtLAST and not suffer from cross-pole or anything. Getting back to the instruments, so these are our optics. This is the simple M3 that selects the instruments up on this pedestal. basically what we were doing was trying to maximize receiver cabin space so we can serve all these science cases. And this is me installing something on Apex. So I was up in this little nook. This is back in 2012. I was up in this little nook high at 5,100 meters elevation, for hours, tying our instrument up with various nooses and fisherman's knots and stuff like that appropriately. And this is in the receiver cabin of Apex where you have to go through 7 or 8 mirrors. So it's really a bear. And then this is just the opposite case where we can put a nice large instrument and not have to worry about like squeezing into tiny spaces and all of that. So that's nice. And then this is just, for scale, that's me. So I'm this tall. And that's how big, like, one of our receivers, one of these red receivers will be the size of one shipping container there. You can make them smaller, but, you're allowed up to that size essentially. And then the blue ones are 4 or 5 of these. So it's really cool. We also have a mechanism for installing these instruments. So basically you put them on this little contraption on rails with an elevator and you can slot them in. And you'll notice there are doors on this side, so you clear the tower, move the telescope 90 degrees and bring it in there if you need to bring it in there or on the other side, etc. And the basic instrument concepts are, we studied these. This was in an AtLAST memo by Elke van Kampen. But looking at the multichroic cameras with polarization and numbers of pixels in there, we really want to get into the megapixel regime ultimately with the multichroics. But first steps first. An IFU for probing all of these lines across there. So an IFU is an integral field unit. Does everybody know these terms? Okay, good. Just making sure. So then you can map the spectral universe. Heterodyne arrays, so these are typically more modest because the readouts are much more complex, but it's discrete amplifiers and gives you high spectral resolution in the end. And then multi-band single pixel receivers where we could participate maybe in EHT, so the Event Horizon Telescope, and contribute to that effort, which is going toward multiple frequencies at once and all sorts of stuff that is really, really well suited to single dish campaigns rather than, say, ALMA, which has a hard time doing multi-frequency or doesn't do multi-frequencies, but it would be hard to upgrade to do that, especially on 50 intense. So some possible instrumentation, I already relayed those. But as far as continuum detectors, we made this nice plot of a lot of the premier instruments over the years and put it on there and fit a sort of scaling relation to the baseline of instruments over the years. And it's not far off where we're actually in the megapixel regime, so 10 to the 6 detector counts. And over the 30 years or more of AtLAST, we would actually get into the gigapixel regime. So that's, that'll be nice. And you really want a telescope platform that's upgradable over this time scale. So if you think back, I showed telescopes that were built in the 80s before there were even single pixel bolometers. And right now, NICA 2 fills the full field of view of the IRM 30 meter, but it wasn't until 2015 that it did that. So the telescope was designed for upgrades already, but now we want to really maximize that and look to the future and allow for even much more transformative instrumentation to come. This is basically how we do this. So this is down in the details, but carbon fiber secondary allows you not to have an active surface there because carbon fiber is pretty stable thermally. We would also have a carbon fiber backing on the tertiary mirror and then aluminum tiles on there. So you can just basically set the panels once so it's flat and forget about it until you need to adjust. But the primary mirror is just huge and it's out in the open. So we did full finite element analysis modeling of this and all of the modes, but basically you see distortions with gravity. Gravity is a known force, so you can correct for that. You just develop a model and apply the gravitational model as you move your telescope. The secondary is within spec for 7 microns RMS, so you don't need to correct for that. This is how the panels are all designed. So they're basically a bunch of tiles, 16 tiles for the typical panel, and with a carbon fiber sandwich base plate and a frame, and then basically actuators for allowing you to adjust that. And it's only 400 panels, so it's about half the number of panels of the ELT for reference. So it's a simpler system in so many ways. And then as far as keeping it in focus, we have various ideas for metrology. So who here is observed with like the IRM 30 meter or the GBT or... So the IRM 30 meter, it doesn't have an active surface, so you can only correct the beam by moving the secondary a little bit. With the GBT, the Green Bank telescope, and the SRT, there's an active surface, but you don't have live measurements of what the surface is doing. So you have to do this thing called astroholography. You look at a source, map it, and put it into a bunch of out-of-focus positions and fit these polynomials to figure out what the surface is doing. And in between observations of your calibrator, you don't actually know what the surface is doing, so the beam can go to hell, essentially, during your observations. We want to avoid that, so we're going to have laser metrology potentially for one of the measurements, so we measure the dish live and correct for it in real time. Or we use depth sensors, which are more similar to what the ELT is using, or we use a millimetric wavefront sensor at a different frequency than AtLAST is observing, and just correct for the dish there. But that basically means you always know what your beam is doing, what your surface is doing, and just keep it in focus at all times, which is going to be nice. AtLAST also, we have this high scan speed requirement. So you can see the typical position changing in a map. The velocities are up to 2.5, 3 degrees per second in velocity. And the accelerations are really large for a structure of this size. That ends up giving you peaks of close to 1 megawatt of power being drawn during the highest acceleration period. And that's a lot, right? The typical approach for that involves basically you use your motors as your braking, and you have a braking resistor. So you slow down the telescope and dissipate all of this current into a resistor that gets hot, and you have to dump the heat to the environment and all that. But I have a hybrid car, right? And that car recovers some of the energy during the braking. So as head of the work package, I said, like, why don't we do this in telescopes? And they're like, Tony, that's not a stupid idea. And they actually did the proper engineering and figured out a way to use this DC-DC converter and to charge up a supercapacitor. So rather than batteries, because the currents are so large, Alexei Kiselev, I should give credit to him. He wrote the paper on this, he did the study. He found out, you can't charge batteries fast enough. You can't, and they have a limited life cycle. The currents are too high. Your batteries might explode or whatever from all of the current drawn and dumped into them very fast. So you use supercapacitors, and supercapacitors had a breakthrough a few years ago where it's very low series resistance. So you can charge them up and discharge them very quickly. So this is cool. And he did simulations, and you could get 80% of your energy back that is normally wasted as heat, and that you have to cool down the braking resistors as well. We didn't even account for HVAC systems that would have to cool that. And this is a simple system that you could actually implement in basically any telescope now. And we're actually going to do that to Apex in this cycle. So that's cool. So the next steps, we finished our first phase design study. We're doing the development project now. It involves a lot of partners around the world, funded contributors and in-kind contributors. So, Spain is on this map, obviously, and we hope to expand this to more partners, of course. We're also merging the Japanese had a concept for the large sub-millimeter telescope that they've been pushing for a while, and it was 50 meters. They're happy with our design, so we're merging projects and going forward with ours because ours is bigger field of view, higher frequencies, and a lot of other cool things. So that's cool, and we're excited about that. And we're moving towards actually prototyping some of these things, you know, and testing the energy recovery system in the field, testing our metrology concepts, testing a lot of things, and advancing the science cases, advancing the operations, you know, program, advancing the tools for forecasts, and there's a lot of room to get involved. You know, there's a lot of work to do, so anybody who's interested and excited about this should get involved. And that's it. So thanks.
Thank you, Tony. Thank you very much.
I don't know.
Any questions?
I went very fast after all. I thought I was running out of time. So I can go back to any slides if anybody wants to see them.
That's okay. There's some time for questions if you have. Yeah, Shane?
Maybe just radio telescopes, maybe in particular, have a history of being overly optimistic on when they're, you know, finally constructed and ready for use. So I'm wondering, is like all the funding already in place, or you're dependent on external collaborators, or how do you think things might shape in the future? Or?
That's a very good question. That's a better question for Claudia Ciccone, who's the manager of the project, but she's looking at, you know, how to actually make it happen politically, how to build the consortium that builds it. As far as, so the construction should take less than 5 years if we had the money, which we don't, right? But if we had the money to build it, it costs about the same as the LMT 50 meters. So it's just like a design change, essentially, but the same amount of metal with, you know, 1,000 times the mapping speed of LMT for the same cost. So if we had that money, we could just build it and have it on Sky in 5 years. That doesn't get you an operations budget. That doesn't get you, like, the support infrastructure. You know, maybe we need a building right next to it for, you know, servicing components and all of that. And, you know, we need more than just the raw structure that's, you know, maybe €250 million to build. You know, we'd be more happy with about $1 billion, you know, to like really put in like a multi-year operations plan from the start and support infrastructure and build some of the first generation instrumentation and all that. Right now we have €4 million to study the, you know, the development and all of that. So that's nowhere near what we need, right? One of the possible paths is ESO's looking for its next project after the ELT. Maybe they'll be interested. Maybe, you know, Spain is part of the ESO community. There are a lot of ESO member states with users who will be interested in this thing. Another thing is, you know, building our own consortium, building something, you know, in partnership with Japan, Taiwan, Thailand, collaborators around the world, you know. So people on this map who are interested, getting them to fund a consortium and build that. Maybe convincing ALMA that it's in ALMA's interest because, you know, ALMA can do the very detailed follow-up, but it can't do the wide field mapping. But it's kind of an open field, and it's not my specialty to figure out how to fund it, actually. So I'm just sort of throwing out the ideas that have been thrown out. But yeah. We do plan to have a construction-ready design by 2028, by the end of this current phase of the study. So, you know. So yeah, if all things fell into place, we could be on Sky in 2033.
More questions? Well, I have one question, and it's about this energy recovery system that you mentioned.
Mm-hmm.
How easy or difficult would it be to export this to current facilities? Because I guess this can be also, not only for radio telescope, but also for other big telescope. No?
Yeah, exactly. I mean, it should be super easy, right? You see the basic circuit here. You just bridge into this circuit and add the DC-DC converter and, you know, a bank of supercapacitors that will be proportional to the energy needs. But like, for example, the CTA has spinning flywheels so that it can, you know, move to source very fast and everything. Mechanical things fail, right? you know, but if you put in one of these, you could charge up your supercapacitor and then just accelerate very quickly to whatever source you had. You can do the same, you know, I think the ELT is looking at this type of technology as well with a mechanical flywheel. My opinion, expressed here, you know, my own views, is they would do better with a supercapacitor and DC-DC converter, but basically any telescope. I also heard after we submitted this article and had, you know, done the revisions, that SPT basically has this in place, and they still just use the braking resistor. They don't have supercapacitors, but they have a mechanism for charging up batteries and recovering some of the power, and they just don't use it. I guess because they have diesel to burn down at the South Pole. You know, I don't know why they're doing this, to be honest. But this would be a simple upgrade to basically anything there, and I hope that people adopt this.
Because it should
Yeah.
save a lot of energy
Yeah.
on the long run, no? The operation.
Yeah. And so like with survey instruments, you know, we're also doing, part of our study is to look at it for the SRT, the Sardinia Radio Telescope, which is a 65-meter structure, and they do spend a lot of energy. They don't scan as fast as us, but anytime you slew, you can also recover the energy and store that for the next time you slew to a new source. For survey telescopes like CCAT and Simon's Observatory, you know, they're just going to spend all day and all night going back and forth. So that's a simple sinusoid where you can recover, you know, most of the energy, use a lot less. And yeah, I mean, I didn't even mention AtLAST. We want from the start to be fully powered by solar energy and have, you know, storage there for our solar energy. So we're also studying that in the second phase, how to implement it and make sure that we have a working system at altitude for this. Yes. Most of the use cases on Earth are not at 5,000 meters. So most people haven't really looked at this.
It's a difficulty.
Yeah.
Not
But,
small.
but Apex and Simon's are both building these types of systems, you know, and we want to scale up and potentially use hydrogen or something more efficient for our power, for the energy storage.
I can ask maybe a scientific one, if you know
Sure.
off the top of your head, what sort of regimes of the warm hot intergalactic medium the telescope could potentially detect, as in terms of maybe gas densities and temperatures?
Anything that's ionized, right? So with the kinematic SZ, so kinematic Sunyaev-Zeldovich effect, if it's ionized gas, it'll have some electron opacity, and that'll produce a Doppler shift on the CMB. So then you need some complementary optical spectroscopic data, ideally, for disentangling the peculiar velocity there. But you can do stacked KSZ. You could also do stacked CMB lensing, you know, for filaments. For KSZ, the reason I mentioned stacking is I know it's less satisfying to stack sources. It's much nicer to just have a direct map of something. But when you stack KSZ, you can cancel out the primary CMB and just get the KSZ component, because, you know, you're basically subtracting things that are difference pairs where you know the velocity and can bring out the signal that way. And then the thermal SE effect, it exists at 10 to the 5 Kelvin, but, you know, for anything that's ionized, but it's a lot weaker because it goes like the pressure in the medium. So we've detected some of these filaments, you know, that are more like 10 to the 6, 10 to the 7 Kelvin in stacking and in a few direct observations. But that one's harder because you get to the lower gas densities and lower temperature stuff. But yeah. I would say, you know, I mean, I think this is why this is one of our major science drivers, is really mapping where the baryons in the universe are, because so much of the universe is just fully ionized gas, wherever that was, in these nifty things. So.
Do you have any specific target in mind? Or?
I mean, I have my own list of favorite clusters. Yeah, I don't know, I guess. You know, there's some really cool mergers, like there's the El Gordo merger, so it's the most massive cluster we know of above redshift 0.8, and it's it's a nice binary merger, but it should have some out of the plane of the sky component that you could measure the kinetic SC effect from as well, and like really say something about the merger dynamics. So I would target that one for sure. And similarly, it's hot enough. Do I have the plot of the SC power spectrum or the SC? Nope. Okay. Well, yeah. If you have multiple frequencies, like we should, with AtLAST going up to 900 gigahertz, 950 gigahertz, you can actually probe the temperature uniquely with relativistic corrections to the thermal Sunyaev-Zeldovich effect, and you can do that without any X-ray information. So that would be really cool, especially for these very hot systems that are, that are out of band for Chandra or XMM or E Rosita or any of these things.
And are there any questions online?
Ooh, there's something in the chat. Should I?
I don't know if it's
Okay.
something at the beginning.
Yeah.
Well, no?
No questions? What would be the contribution of AtLAST to the Event Horizon Telescope?
Well, yeah, so nobody's actually looked at the science case yet or done simulations, but there's a logistical contribution. So often it's hard to coordinate the use of ALMA and single-phased array for EHT campaigns. They still have to propose every year, to get time, and if the time's not awarded, then ALMA would be missing from the EHT campaigns. So we could set up an MOU with AtLAST where they get their campaigns, right? It's a huge collecting area. If you want to do multi-frequency EHT, which they do, they want to do 3 or 4 bands simultaneously, you would have to split up the ALMA array and have 12 antennas doing one frequency, 12 doing another, and another with different phased arrays. I don't know if the ALMA correlator supports doing that kind of array phasing at multi-band frequencies, so it might not even be feasible. But putting multi-band receivers on ALMA would be extremely expensive, and if you do it on AtLAST, you just need one. And it's a third the collecting area of ALMA, and the EHT is not signal starved; it's mostly baseline limited. Right, so yeah, it's sort of a no-brainer to put a receiver on there and coordinate with EHT and contribute to this fundamental physics thing. I'd really like to see people actually simulate this and make the case, and also talk about space VLBI, and contributing to that, because a nice terrestrial ballast for those measurements would be awesome. Yeah.
I had a very good question. One thing before the acronym or the name? AtLAST, or did you have to hold the name?
Oh no, I just call it AtLAST. Anything that's a pronounceable word, I just.
What came before the acronym, or search something?
Yeah,
acronym, or the other way around?
It was simultaneous. Like we were looking for something descriptive that could also be said as a name. So, yeah.
It came at last.
Yeah, it's kind of, so my postdoc at UPenn, I worked on the balloon-borne large aperture submillimeter telescope, so BLAST, which is kind of a terrible acronym for something, because balloons often crash or explode or spin out of control or whatever, right? But the LAST is the same for AtLAST, so it's the Atacama large aperture submillimeter telescope instead. And yeah, so.
We have one question from Ricardo Rito. Can I mute your microphone? Ask your question, Ricardo.
Is it going to come through here? Is the hello?
Ricardo. Ricardo.
Okay. Now you can hear me?
Yes. Okay.
Or perhaps quite slow. So, first, thank you for the nice talk. I'm really impressed with the telescope. the numbers, the idea is really impressive.
Thanks.
So the question is very simple. Did you manage some timeline for the whole project? So I understand that you are going step by step and you are in the
Yeah.
the definition still. But what's the whole timeline?
Ooh.
Sorry,
Yeah, there's
I
a lot
need
of,
my microphone.
Okay.
Or-
So we don't have a definitive timeline yet. It's more taking it step by step. We have the current phase funded for 3.5 years. We started in January, so mid 2028 we'll have this construction ready design. And it really depends on what the funding scheme looks like, who's going to actually fund it and build it, whether it's adopted by ESO or any other consortium. And then, we're building it to be as long-lived as possible because, building new telescopes every few years is not really sustainable. So we want to build it, to be a long-lasting structure, like well over 30 years of timeline. So I mean, that's just the rough idea that we have now. But yeah, it's all it's all just optimistically hoping that we can get things in place for funding by 2028 and have it on Sky in the early 2030s, 2033.
Steve, I think.
Yeah.
Okay, thank you. Yeah. I understand it's hard to estimate the specific times with more detail. Could you give us more detail about in which aspect can we specifically contribute to the project, or can we join some way to the project as a whole? That's the last question. Thank you.
Yeah. So science forecasts are one. If you're an astronomer and have a favorite science case, using the various tools. We have tools for simulating bolometer observations, tools for sensitivity calculation, tools for simulating the direct detection spectrometers cases, but like making concrete forecasts and saying like, okay, we can do this observation. It'll take, this number of detectors and this number of hours, months, years, whatever, to achieve this science goal. Like really firming up the science forecasts is crucial. Get involved in it depends what your area of expertise is. It's going to need a lot of instruments, a lot of very large instruments that are difficult for small university groups to build. But in a large collaboration, people can contribute multiple components and bring it all together. And all of that. There's, operations work package.
Operations, we always need people contributing to operations because there's a lot of work to do.
Yeah.
In several aspects like data management, data reduction, operation schemes, maybe inherited from other places, from other observatories.
Yeah.
So there's, of course, plenty of ways of contributing. And then if I can mention something, maybe just be aware that there is this newsletter that is once in a while circulating with the latest news on the developments of the project. So you can stay tuned to what's going on, meetings, developments, and then contact any of the teams that are working currently the project, which I think will benefit from more people.
Yeah. So it really depends on what your interests and skills are. I guess just if you have interest, get involved. We started very grassroots, right? So it was just everybody contributing out of their sort of love for this project and this idea, right? And we still rely on a lot of in-kind contributions for everything. We don't have like some big czar of astronomy, like driving things, and like dictating what everybody does, from a top-down level. We're really like bottom-up, grassroots effort, which I think is, at least to me, was more appealing. And yeah. And also, if you know any politicians, talk to them. Tell them how wonderful this will be, and how. I mean, most of the light in the universe is at millimeter and sub-millimeter wavelengths, actually, and we should be looking there a lot more. And right now, we aren't. Most of the new telescopes are in the visible regime, which is great, which is lovely, but we should also be looking at other wavelengths to get the complete picture, of the universe. So, yeah.
I think we can stop here. Let's thank Son again. Thank you all for joining us.
Sure, thanks.